Andra, eh. Mark, Mark. Good day, everyone. Today we will discuss our performance innovative task in engineering data analysis. In this discussion, we explore the probability of structural failure in a building over the next 2 years, focusing on key risk factors such as earthquakes, material fatigues, and extreme wind loads. The engineer uses historical data and mathematical modeling to estimate the likelihood of failure, applying both the union of probabilities and the binomial distribution. This method allows us to access the cumulative risk from various environmental conditions, traffic loads, and the aging of materials. By analyzing each factor independently and then combining them, we can gain a clearer picture of the building's overall vulnerability. This approach helps identify the most critical threats to the structure, guiding decisions on maintenance, reinforcement, or other preventive measures to reduce the risk of failure over time.
Objectives: to determine the individual probabilities of failure for each cause over the 2-year period, to calculate the overall probability of at least one structural component failing, considering the independence of the factors, to analyze the potential failure scenarios using a binomial distribution if there are multiple identical components, to provide insights and recommendations for risk management based on the evaluated failure probabilities.
Statement of the problem. The structural integrity of a building is critical for ensuring the safety of its occupants. Over the next 2 years, the civil engineers must evaluate the failure probability of the building structural components, namely beams and columns, due to the three primary factors: earthquakes, material fatigue, and extreme wind loads. Each of these factors has the potential to independently contribute to structural failure. So here are the graphs and result of our data.
For environmental condition probability, for a range of 70 to 90, we use a constant of greater than 75, indicate a high risk factor. Months with high probability indicate critical times where environmental conditions are particularly unfavorable, necessitating focused risk management efforts. Over the next 2 years, the failure of probability due to environmental conditions is approximately 20.83%.
Traffic load probability. When talking about probability of failure due to traffic load, it is helpful to think of it in terms of how much stress the structure can handle before things starts to go wrong. In this case, we're looking at a range between 40,000 and 50,000. At the lower end of that range, the structure can manage the traffic fairly well with little risk of failure. But as traffic load gets closer to 50,000, the chances of something going wrong increase. It is similar to how a bridge, for example, can handle a certain number of cars and trucks at once. But if the traffic becomes too heavy, the bridge starts to experience strain. If the strain keeps building over time without being managed, it could lead to failure. This is why keeping an eye on the traffic load is so important. If the load regularly gets too close to the upper limit, we might need to take steps like diverting traffic or reinforcing the structure to prevent any damage. In short, this discussion is really about balance, finding a way to keep the structure safe while handling the demands of heavy traffic. Regular maintenance, monitoring, and traffic management are key to making sure the load doesn't reach a dangerous point.
Material fatigue probability. Over the 2-year period, the assessment of material fatigue focuses on the cumulative effects of repeated stress and wear on the material's integrity. During this time frame, factors such as load condition, frequency of use, and environmental influence can significantly impact the probability of failure. For instance, if the material is subjected to high traffic load or extreme environmental condition, its likelihood of failure may increase markedly. Engineers can simulate various scenarios to predict how the materials will perform over these 2 years, utilizing the probability scale of 0 to 1, the quantifier is. A high probability indicates that the material is likely to fail within the 2 year span, promoting consideration for maintenance or replacement. A lower probability suggests that the material is likely to withstand the stress encountered during this period. So, this analysis is crucial for effective planning and ensuring the safety and reliability of structures that rely on the materials in question.
The overall probability of failure for the building's structural components over the next 2 years is approximately 4.1%. By using the binomial distribution, the engineer can further analyze the likelihood of specific failure outcomes during inspections or assessments. This approach allows for a comprehensive evaluation of the risk involved and supports informed decision-making regarding design, materials, and maintenance strategies.
The relationship between economic condition, traffic load, and material fatigue is interdependent. Economic growth often leads to increased infrastructure developments, resulting in higher traffic volume that place greater stress on transportation system. This heightened traffic can accelerate material fatigue, cause quicker deterioration of structure. Strong economic enable investment in higher quality materials that better withstand fatigue. Thus, a decline in infrastructure due to material fatigue can negatively impact economic condition by rising transportation costs and reducing efficiency. Understanding this interconnectedness is crucial for policymakers to make informed decisions regarding infrastructures, investment, and maintenance.
Conclusion: evaluating the probability of failure in a building's structural components due to environmental conditions, particularly temperature variations, is critical for ensuring safety and durability.
Based on the given traffic load range 40,000 to 50,000, the probability of failure due to excessive traffic load is being modeled. This data suggests that within this range, the structure are subject to increasing stress, and failure becomes more likely as traffic loads approach the upper limit. Essentially, higher traffic volumes create greater strain, which heightens the risk of structural failure. It is important to monitor these load levels to prevent overburdening the structure and ensure long-term safety.
The probability of material fatigue failure depends on factors like material properties, loading conditions, and environmental influences. Utilizing statistical methods allows engineers to predict lifespan and enhance reliability in designs. Continued research in material science will improve our understanding and management of fatigue, leading to safer and more durable structures. And that would be all. Thank you.